can do more fun stuff. Namely, we can actually start talking about stochastic processes. Okay, so far we've stayed with random variables, so very static picture. Now we can start having the idea of having a time in our picture. And it's lots of fun. Okay? So we'll have an argument, which will have the role of time. Okay? So far we had a probability space, right? So there's one sigma algebra which represents our information at somehow the end of time. So if you know, this is my final sigma algebra with respect to which everything is measurable. Now I'll introduce the notion of filtration. So filtration is a sequence, an increasing sequence of sigma algebras. In F. Okay, but what I mean by increasing? For inclusion. So I mean this is a family Fn, or n greater than 0 or 1, such that Fn is included in Fn plus 1, and that's all included in F. Okay, so they're all sigma algebras. And the interpretation is that this is time, and this is the information available at time n. We'll play around with this parameter a little bit. Okay, so we'll talk about things where maybe instead of going up, the time goes down, sort of is decreasing. And maybe I'll just mention at some point what happens if this is not, this is not an index from a well-ordered set, etc. So lots of things can happen. And in continuous martingales, you'll be playing with t, which will be from an interval or half line. Okay? But for now, we'll just talk about that. So if this is the information, then, well, let me define what a stochastic process is. So a stochastic process X is a family of random variables. So in itself, it's nothing too exciting about stochastic process. And you'd notice that when we talk about variables, we use random. And when we talk about processes, we use stochastic. They mean the exact same thing. They come from Greek and Latin, but otherwise, or Latin and Greek, but they really mean the same thing. Okay? So stochastic process, Xn, just a family of random variables. So the interesting thing is when we combine this with the idea of having information. So we say that this process X is adapted if Xn is Fn measurable. For all my times. So it's adapted to a given information. So remark, if I don't start with information, but I start with a family of random variables, okay, then of course I can build a filtration to which it is adapted. So X is adapted to fxn, which is defined as the natural filtration. So something that's generated by the process itself. By definition, this is a filtration, and we know this is the smallest filtration to which x is adapted. Okay? This notion of being adapted really depends on the filtration. So I would invite you to sort of try to play around with it. You can build examples of x, which is adapted to a filtration, say it's natural filtration. You can build examples where we have where if you take sums of say processes, then you can see that the natural filtration will be quite different from things. So this generating here the natural filtration, of course, is very specific to my process X. In particular, I know if I have a process X and I take minus this process, then X minus X will be just a boring process always equal to 0. Its natural filtration will be trivial. So there's no linear structure or sort of vector space structure in the natural filtration. On the other hand, of course, if I fix filtration, then the space of processes which are adapted to it, this is a linear space, or a vector space. I can take linear combinations of such processes, and that's just the property of measurability, that a linear combination of random variables which are fn measurable is still fn measurable. Okay, when the fun really starts, I think, is when I think about time. So this index is n. So for the moment being, I've used integers. Okay. But of course, now that I have randomness, I can also start, and I have a process, I can start to think about instances in time which are a bit less boring than just integers, but which themselves are random. So we could take a time the next time I see you, okay, which is likely to be tomorrow, but who knows, maybe I'll bump into you in the corridors before that. Or I could take the coldest day in December in Oxford. Okay, somehow we'll be looking at the temperature Carfax at noon, and we'll be recording that. Okay, so I don't know when this will happen, and you see that this is already quite different, right? So the next time I see you is something that we both know will happen when it happens. We don't know when it will happen, but when it happens, we know it happened. The coldest day in December, well, we sort of have to wait until the end of December to realize, oh, it was on the 2nd of December. So it's the first type of times that I'm interested in. I'll be calling them stopping times, and these are the sort of random times, but we have this property that when they happen, we all know they happened. And of course, by we know, I mean people who have the given set of information. Okay? So this is our definition of a stopping time. So there's sometimes also called, you may hear people saying Markov times or Doob time, but I'll stick with stopping time. So a random variable, tau, which takes values in 0, 1, 2, all the integers plus infinity, is called a stopping time if the following happens. So what does it mean that tau happens? It means that tau is equal to n. And what does it mean that we both know that it happens? It means that this is fn measurable. So this is the information I have at time n, and this information alone is enough to ascertain that tau happens at time n. remark. Of course, because Fn is filtration, so Fn minus 1 is included in Fn. That means that if I look at the set tau less or equal than n, which is equal to union tau is equal to k equals 0 to n, all of these are in Fk, which is included in Fn, so this whole thing is also in Fn. So I could just, this implies that this set is in Fn, and you can show that the converse also holds, right? So you could replace this by saying tau less or equal than n here. Or we could replace this by the complement of tau less or equal than n, which is tau strictly greater than n, which means at time n, we know this hasn't happened yet. Right? So stopping time is very much relative to the filtration, just like the notion of adaptness is. It's quite important. So some examples or simple statements. So let f omega f fn p be a, and I'm going to call it a filtered probability space. So filtered probability space, it has nothing to do with filtering, it just has a filtration. Okay, so it has a filtration fixed. Then tau of omega equal to n for all omegas in omega. So this is a deterministic random variable which takes an integer value, okay, is a stopping time. So deterministic times are stopping times. Okay, and then second, if tau and rho are stopping times, then min tau rho and max tau rho are also stopping times. So if I have two stopping times, the next time I see you, and the first time that, I don't know, the share price of Rolls-Royce on London Stock Exchange reaches price n, okay, then the first time of the one of those happens, or the time when they both happened, they're still stopping times. So this is quite trivial. I'll leave it as an exercise. It's still true in continuous time, but it becomes much more, well, a little bit more difficult to show. Okay, so those sort of things, you'll be redoing them for those of you doing continuous martingales. You'll be redoing them in continuous time, and you'll then appreciate how much simpler it is when your time set is distinct integers. So you have spaces between your times. Things are easier. For us, a more interesting example which will be almost the only example we'll need, is the following. So let x be adapted on a given filtered probability space. And let B be a Borel set in R. Then the first time my process X visits set B is a stopping time. So I'm going to call this the hitting time of set B. Okay. So what is this? This is the first time that Xn visits set B. Where if this never happens, then this is defined to be equal to infinity. Okay? So inf over empty set is equal to infinity. That's why in my definition of the stopping time, I allow the value plus infinity, and somehow the interpretation is that, well, whatever my property was that I was trying to see if it happens, then somehow it never happened. is a stopping time. Proof? Well, this is quite easy. What do I have to show? I have to show that tau equals n. So what does it mean hb is equal to n? Well, this is the intersection of the following things. So from k equals 0 to n minus 1, xk was not in B. Okay, so I had to take values from outside of B, and then xn was in B. So it's just an intersection of n sets. All of them are. So what do I know? How do I know that this is in Fn? Well, this is an Fn measurable random variable, xn, so this by definition is in Fn. And these are all xfk measurable because x is adapted. So this is fk measurable, but again, xfk is in Fn because I have filtration. Okay. So all in all, this is in Fn. Good. So we had this notion of filtration, right? Just an increasing family of sigma algebras which encode the information that we have at time n. A natural example was given by the natural filtration of x, which is simply the information flow which is generated by my process. This is what I learned from observing the process. And now we also have this notion of stopping time, which is like a strategy, which is a random time, but which has this property that when it happens, we all know it happens, or everybody who has the information set Fn knows that it happens. So what is now the information that's available to me at time tau, when tau is the stopping time? I should be able to, it's a question which makes sense, right? How much do we know at the time where my stopping time happens? I guess I should first tell you what f infinity is. So this will be just the sigma algebra generated by union of fn's. Okay. So this could be equal to f or could be smaller than f. But if I have a filtration, then I'll always put f infinity as the sigma algebra generated by all the information in my filtration. Okay. And I need this sigma algebra, remember. The intersection of sigma algebras is a sigma algebra, but the union of sigma algebras is not necessarily a sigma algebra. So I need to hit this with a sigma. So what is f tau? So these will be those set in f infinity, such that what happens? Well, that if I intersect my set with tau equals n, so I know that my tau happens at time n, then whatever this set was has to become Fn measurable. Okay. The right-hand side is a definition of family of sets. You would verify this as an exercise that this is a sigma algebra, and so it sort of makes sense to define this, and I claim this is an f. Sort of makes sense to call it f tau. And why it makes sense is the following proposition. Okay, so I have tau as stopping time on a given filtered probability space. Actually, let me take it two stopping times. Stopping times. So then first, this is what I've said above. F tau is a sigma algebra. And second property is that if tau is less or equal than rho, then F tau is included in F rho. And this is, again, a very simple exercise. From the definition, you can easily check this. But fundamentally, this is a very interesting property for us, because it says that if I had the property of filtration, then this is preserved when I now look at random times. And this is really what I would like to do. A world in which we look at discrete time, so day by day, becomes very boring. Okay? I'm interested in thinking about stochastic processes, so thinking about random evolutions simultaneously at all possible random timescales. And a random timescale, well, this will be some sort of sequence of random variables, which I'll then interpret as first moment in time, second moment in time, third moment in time. Okay? And what I want is that for them to be a random timescale, they need to be ordered. So I need this property here. So in particular, combining this with this statement here, okay, you see that F tau min n is a filtration included or smaller than my original filtration Fn. Right? Why? Because the constant time n is a stopping time, so tau min n is a stopping time, and now tau min n is of course less or equal than tau min n plus 1, etc. Right? So I get a filtration property from here. What is this filtration? Somehow intuitively, it's the flow of information, but which stops at the time when my tau happens. Okay? If I have an adapted process, I can define what it means, the value of my process when my stopping time happens. Right? I can look at something that takes omega in omega and associates with it x tau of omega. That's a number now. So x with a number makes sense of omega. What is less clear is that, so this is a function. Now the question is it measurable and in what sense? Now this is f measurable. So it's a random variable because x minus 1, so x tau, okay, let's call this x tau, minus 1 of set b will be just equal to union over n's, tau equals to n, because tau has to be equal to something. So tau equals to n is tau minus 1 of my integer n, and now intersected with x minus 1 n of b. So again, because this is a countable union, I have no problem defining this. You can already see that if this was an uncountable set of times, I'll have to do something smarter. Okay, I'll have some troubles at least. Here I have no troubles. This is a countable union of sets. They're all in F. Okay. But in fact, I can do better. I can do F tau, which is what I want. Okay, so x tau, the value of my process when my time happens, is actually measurable with respect to my postulated way of understanding the information at time tau. So let's call this let's write this as a proposition. So let x tau be x tau min n. And I'll call this the stopped process. Is this clear why this is the stopped process? You know, if you're thinking about simple symmetric random walk, and your tau is the first time you reach level 1, 2, 3, 4, 5. Okay. Then this might take you a long time. Here. This is tau of omega 1 for xn of omega 1, right? But maybe on another path, you went up, 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 down, up, and you were already here. Okay, so this was tau at that point. Whatever happens if I stop my process, that means that from that point onwards, my process becomes constant and nothing changes because I don't see the evolution anymore. Okay? So that's the stop process. Where tau is a stopping time, and x is adapted. Then I claim that x tau is fn or tau min n adapted. Okay. Really, this is the same statement as saying that x tau is f tau measurable. Okay. Which is what I'm going to prove. And then you can apply it to any stopping time. So let's maybe write it x rho is f rho measurable for any rho a stopping time. So what does it mean to show that x rho is f rho measurable? This happens if and only if, well, the pre-image of a Borel set is in here. Okay. But that's difficult to show. So we know that this is the same as saying that x rho less or equal than x is in f rho for every x. This we know by pi lambda systems lemma. Right? Which hopefully by now you have internalized and this became sort of your best friend. But each time we make such a quick jump, we're using this time and again. And what does this mean? X rho is less or equal than x belongs to f tau. Well, if I look at the definition, this means this happens if and only if. And in this definition, this is for all n's, right? I have to have this property for any n. There was no n on the left. This has to be true for all n's. So if and only for any n, x rho less or equal than x intersected with rho equals n belongs to fn. But of course, this set is the same. Once rho is equal to n, this is the same as saying xn is less than x intersected with rho is equal to n. And that belongs to fn because my x was adapted. And that belongs to fn because my rho was a stopping time. And I'm done. Okay, so we'll stop here. We essentially introduced just a couple of notions, and then all the proofs were, very simple one-liners. But quite a lot happened in this lecture, okay? Because we introduced time, so we actually let time run. And then we realize that time doesn't need to be boring, sort of deterministic 1, 2, 3, 4, 5, but it can be random and composed of those random variables which are stopping times. So they could be first hitting times of levels, etc. We just have to know that they happen when they happen. And that we can extend most of our natural notions from having boring integer times to this very much richer world where times are random variables themselves. And we'll see that a lot of power of martingale theory will come from the fact that martingales, which we define in this sort of simple discrete time, actually are martingales still on arbitrary timescales given by stopping times. Right, I'll see you tomorrow. Thank you.